questions the universe throws our way. Today, we're diving into a really profound idea, one that's often misunderstood: how energy and matter might actually converge upon a single point in space-time. We'll be looking through some fascinating sources, especially one called cosmic convergence, from Big Crunch to black holes.
hmm
It provides this incredible analysis of gravitational collapse, from the scale of stars right up to the entire universe.
Right. And our mission today is really to cut through some of that complexity. We want to unveil what scientists actually mean when they talk about convergence to a single point.
Hmm.
We'll look at its history, how our understanding has, well, dramatically shifted, and what it means for how we see reality.
And trust me, you're in for some surprising twists. What we once thought was pretty much a foregone conclusion about the universe's fate, it's been completely upended by new discoveries. So if we're going to grasp this idea of cosmic convergence, we really have to start with the true game changer, Albert Einstein. Okay, let's unpack this. His general theory of relativity, back in 1915. It didn't just tweak Newton's idea of gravity as like a simple pulling force. Einstein basically rewrote the rulebook. He showed us gravity is actually a geometric property of the universe itself, literally the shape of spacetime.
Exactly. And what's truly revolutionary here is that Einstein showed space-time isn't just some passive stage, where things happen. It's actually a dynamic four-dimensional fabric. The core idea is often put as matter and energy tell space-time how to curve.
And curved spacetime tells matter and energy how to move.
Right. Precisely. Think of like a bowling ball on a stretched rubber sheet. It makes a dip. That dip is the curved space-time. And if you roll marbles nearby, they naturally move towards it. They're following what we call geodesics, basically the straightest paths possible through that curved landscape.
And the mathematical heart of all this are the Einstein field equations, the EFE. These aren't just formulas, they're kind of like the universe's instruction manual for gravity. They show gravity isn't just a force, it's this self-propagating feedback loop, which is pretty mind-bending. It's the engine behind things like black holes.
Absolutely. And to really get their power, let's simplify the core idea. On one side of the EFE, you have what's called the stress-energy tensor. Think of this as the universe's ingredients list for gravity. It accounts for everything that warps space-time. So not just mass, but also energy density, which, thanks to EMC2, is basically interchangeable with mass, but also momentum, pressure, even the flow of energy.
Pressure.
Yes, pressure. The big implication is that gravity isn't only sourced by heavy objects. Things like the pressure inside a star, or even pure light, which is just energy, all contribute to warping spacetime. That's a huge departure from Newton.
Wow, okay. So even light, pure energy, is tugging on space-time. That completely changes how I always pictured gravity. So that's the cosmic recipe for gravity. What about the other side of the equation, the actual shape space-time takes?
Precisely. That's where the metric tensor comes in. This is what defines the geometry of spacetime everywhere. It's like the universe's ruler and clock combined, letting us measure distances and time intervals in this warped reality. It encodes crucial effects like gravitational time dilation, time slowing down near massive objects, and spatial curvature, space itself bending.
And then there's the Einstein tensor. This measures exactly how space-time is bending and twisting.
That's right. And its structure is cleverly designed to ensure energy and momentum are always conserved, never lost, which is fundamental in physics.
Okay, and what about that lambda thing, the cosmological constant? That has a weird history, right?
It really does, lambda. Einstein first put it in to force a static universe, which he later regretted, called it his biggest blunder after Hubble found the universe was expanding. But, plot twist, lambda made this dramatic comeback. We now think it represents the intrinsic energy of empty space itself, a kind of repulsive force driving the accelerated expansion of our universe. We now call it dark energy. Talk about a comeback.
It's amazing that his biggest blunder turned out to be so critical to our current understanding. So these equations, the EFE, they're more than descriptive. They're a powerful predictive engine, right? For everything from the Big Bang to black holes.
They absolutely are. And a key reason for that, especially for extreme stuff, is their nonlinear nature, which basically means gravity gravitates. The energy in the gravitational field itself creates more space-time curvature.
A feedback loop.
Exactly. A powerful feedback loop. This self-reinforcing thing is what really sets Einstein's gravity apart. And it's what leads to runaway gravitational collapse. And yes, those extreme points where curvature goes infinite, what we call singularities.
Okay, so given that, let's talk about the most dramatic vision of cosmic convergence, the Big Crunch. For a long time, this seemed like a very real possibility for the end of our cosmos, a huge collapse, like the Big Bang played backwards.
Yeah, you can picture the universe's fate as this kind of cosmic tug-of-war. On one side, you've got the outward momentum from the Big Bang pushing everything apart. On the other, the collective gravity of all the matter and energy trying to pull it all back in. Which side wins determines everything.
And that outcome expansion, forever or eventual collapse, it all hinges on one crucial thing. The average density of matter and energy. We measure this with the density parameter, omega. And the Friedman equations, which come straight from Einstein's work, tell us this density parameter dictates the universe's fate and its overall shape.
Right. So if omega is greater than 1, A1, you get a closed universe. Think positive curvature like a sphere surface. Gravity wins, eventually halts expansion, and pulls everything back into a big crunch. But if omega is less than or equal to 1, you get an open or flat universe. Negative or zero curvature. In those cases, gravity just isn't strong enough. The universe expands forever.
So if a big crunch were to happen, wow, it would be catastrophic. The Big Bang in reverse. Expansion stops, reverses. Galaxies would start blue shifting, rushing towards each other.
Clusters merge, galaxies merge, stars collide.
And the cosmic microwave background, the Big Bang's afterglow, would blue shift too, heating everything up.
Massively. Heating the whole universe so much it could ignite stars before they even hit each other.
Then everything breaks down: planets, stars, atoms, nuclei,
dissolving into this plasma soup of fundamental particles.
And finally, all matter, energy, space itself collapses into an infinitely hot, infinitely dense singularity. The end. So the Big Crunch really paints a dramatic end picture, and for decades that was a leading theory. But then something changed everything. This is where it gets really unexpected, doesn't it?
It certainly does. In the late 1990s, two separate teams of astronomers were using Type Ia supernovae, these distant exploding stars, as cosmic measuring sticks. And they found something stunning, totally unanticipated. The universe's expansion isn't slowing down.
Speeding up.
It's accelerating. This discovery was so huge it got the 2011 Nobel Prize in Physics. And it basically ruled out the Big Crunch scenario.
Wow.
Yeah. This acceleration means there must be some mysterious component out there with strong negative pressure, essentially a repulsive anti-gravity force. This is what we now call dark energy. And later, more precise measurements for missions like WMAP and Planck confirmed it. The current cosmic census tells us our universe is spatially flat, and its energy budget is just dominated by this dark energy. Something like 69–71% dark energy, maybe 24–26% dark matter. And ordinary matter, everything we see and touch, is only about 5%.
So the question isn't just how much stuff, but what kind of stuff dominates. That's key. And given what we know now, the universe isn't heading for that fiery Big Crunch. It looks like it's destined for a cold, dark, ever-expanding future, often called the Big Freeze or heat death. Okay, so the idea of a universal Big Crunch is pretty much off the table based on evidence. But the fundamental process energy converging to a point that isn't just a dead theory, it's happening, right, on a smaller scale. I mean, black holes, these seem like real examples of general relativity leading to convergence.
That's exactly right. Gravitational collapse is the process where an object's own gravity just overwhelms everything else, leading to this unstoppable contraction.
And the most common way this happens is stellar collapse, right? With really massive stars.
Yes. Stars with cores significantly larger than our suns, above what's called the Tolman-Oppenheimer-Volkoff limit, around 2 to 3 solar masses. When they run out of nuclear fuel, the outward pressure just stops. Boom. The core collapses catastrophically under its own weight, crushing down relentlessly to form a stellar mass black hole.
And you mentioned maybe even earlier, in the primordial universe, before stars.
Yeah, it's thought that huge clouds of gas might have collapsed directly back then, forming the supermassive black holes we see in galaxy centers today, maybe starting at hundreds of thousands of solar masses.
So what does a black hole actually look like, according to GR? What are its key parts?
Well, there are two main features. First, the event horizon. Now, this isn't a physical surface you could, touch. It's a boundary in spacetime itself, a true point of no return.
Defined by the Schwarzschild radius.
Exactly. RS equals 2gmc2. Its size depends only on the mass. At this boundary, space-time is so warped that the escape velocity hits the speed of light. Nothing, not even light, gets out once it crosses that line.
And then, right at the center, the singularity.
Classically, yes. That's where, theoretically, all the mass is crushed into a point of zero volume and infinite density, where our classical physics just breaks down completely.
A single point for a non-rotating black hole, or a ring if it's spinning.
Correct. A point singularity or a ring singularity.
Okay, we've used singularity for both the potential Big Crunch and now for black holes. Are these 2 points really the same thing? Or are they fundamentally different? That feels like an important distinction to make.
It's a crucial distinction, and mixing them up leads to a lot of confusion. While they're both called singularities, their physical nature and their causal nature are profoundly different. Think about the Big Crunch singularity if it happened. It would have been a space-like event.
Space-like.
Meaning, it's a moment in time that happens everywhere simultaneously. It represents the absolute end of time itself for the whole universe. It's global.
Okay. And the black hole one?
A black hole singularity, for someone falling in, is time-like. It's a specific location in space that lies in the future path of anything that crosses the event horizon.
So it's a place you go to.
Exactly. Think of it like a cul-de-sac on the cosmic map, a destination you fall into, hidden behind the event horizon. The Big Crunch singularity, though, would be like erasing the entire map itself, for everyone, everywhere. No outside, no event horizon to cross. One is an end in space-time, the other is an end of space-time. Big difference.
Right. So these classical singularities, whether in black holes or the hypothetical Big Bang, they're actually a problem for physics, aren't they? They signal where general relativity breaks down, pointing towards the need for quantum gravity.
Precisely. GR is classical. It doesn't include quantum mechanics. It works beautifully almost everywhere, but it just fails near a singularity. At what we call the Planck scale, incredibly tiny distances, about 1035 meters, and extreme energies, space-time itself should fluctuate wildly due to quantum effects. The smooth geometry of GR just doesn't apply there.
So a classical singularity isn't really a physical thing. It's more like a warning sign saying our theory stops here.
But it's not a dead end. These quantum gravity theories offer some really fascinating solutions. They suggest convergence doesn't just end in, well, nothingness, but maybe some new quantum reality. What are those ideas?
Okay, one leading candidate is loop quantum gravity, or LQG. LQG suggests space-time isn't smooth and continuous. It's actually woven from discrete fundamental loops of quantum geometry, like tiny threads. There's a minimum possible area in space-time. So as matter collapses, it eventually hits this fundamental limit.
And then what? LQG predicts. This triggers an incredibly powerful repulsive force, a consequence of this quantum geometry that actually halts the collapse. In cosmology, this could mean a big bounce instead of a Big Bang singularity. For black holes, the singularity is also replaced by a bounce. It could potentially transform the black hole into a white hole where matter can only escape.
So space-time doesn't end, it just continues through a quantum phase.
That's the idea in LQG, yes. A quantum extension.
And then there's the other big one, string theory, and this fuzzball model.
Right. String theory says the basic building blocks aren't points, but tiny, vibrating, one-dimensional strings of energy. In the fuzzball model derived from string theory, a black hole isn't empty space around a singularity. Instead, the entire volume inside the event horizon is filled with a dense, tangled ball of these strings, a fuzzball.
No singularity, no vacuum inside.
Correct. The event horizon is sort of the fuzzy physical surface of this quantum object. When stuff falls in, it's not destroyed. It merges with the fuzzball, its strings joining the tangle. It resolves the classical singularity problem by replacing it with a complex quantum object.
And these quantum ideas also tackle that huge puzzle, the information paradox with black holes.
Yes, they play a critical role there. The paradox is a clash between quantum mechanics and GR. Quantum mechanics insists information, the exact quantum state of things, can never be truly destroyed. It has to be preserved. We call that unitarity. But Stephen Hawking showed black holes aren't totally black. They emit faint Hawking radiation and slowly evaporate.
And that radiation seemed random, like it carried no information.
His original calculations suggested exactly that it was thermal, random. So if the black hole completely evaporates, all the information about what fell in seems to vanish forever. That's a direct violation of quantum mechanics, a major paradox.
So how do LQG or fuzzballs get around that? How do they save the information?
Well, both offer ways out. In the fuzzball model, there's no singularity to destroy information. It's stored in the specific, complex configuration of the strings making up the fuzzball. That information then gets subtly encoded in the outgoing Hawking radiation, preserving unitarity.
Ah, okay. And LQG.
In LQG, the bounce offers a way out. Information falling into the black hole could potentially pass through the bounce and reemerge from a white hole later on. Plus, there have been recent breakthroughs, even within semi-classical gravity, involving things like the Page curve and space-time wormholes, suggesting information does get out somehow. It's a very active area.
Okay, let's shift gears a bit. Beyond a final end state, like a crunch or freeze, what about models that propose? Well, eternal rebirth.
Cyclic cosmologies. Yeah, the idea of a cyclic universe isn't new. Back in the 1930s, there were simple, oscillating universe models. Big Bang, Big Crunch, repeat. But those early ones had problems, mainly with entropy. The second law of thermodynamics meant each cycle would get bigger and messier, still implying a start somewhere. There are more modern versions, too, like the Steinhardt-Turok model, using string theory concepts like colliding brains triggering big bangs.
But Sir Roger Penrose has a really unique take with his conformal cyclic cosmology, CCC. It's different because it actually embraces endless expansion, right? It doesn't need a crunch.
That's the fascinating part. Penrose's CCC starts by looking at the very, very distant future of our universe, which he calls an eon. After an unimaginable time, like way beyond 10-100 years, the universe reaches heat death. Stars are out, black holes have evaporated via Hawking radiation. And this is a huge assumption. Totally unproven, all massive particles like protons and electrons eventually decay into massless ones.
Leaving only photons and gravitons, massless stuff.
Exactly. A universe filled only with massless particles.
And here's the really wild part, the conformal transformation. Explain that.
Okay, imagine a balloon again. Draw a tiny square on it. As you inflate the balloon infinitely, the square gets huge, distances stretch forever. But the angles within the square, its shape, remain the same locally relative to the balloon's surface. That's conformal invariance angles are preserved, but scale isn't. Penrose argues that a universe containing only massless particles effectively loses its sense of scale. Time and distance become meaningless for them. This infinitely large, cold, empty future universe becomes mathematically indistinguishable via this conformal rescaling from an infinitely small, hot, dense Big Bang state.
It forgets how big it is.
Sort of. The math allows you to smoothly map the infinite future boundary of one eon onto the Big Bang singularity of the next one. It's a mathematical connection Penrose believes reflects a physical reality, initiating an endless sequence of universes.
So in CCC, convergence isn't a physical collapse. It's an abstract geometric transformation at infinity.
Exactly. The universe doesn't shrink. It just undergoes this conformal rescaling, where its vast future becomes the compact past of a new eon.
Wow. Okay, that sounds incredibly speculative, but it is science because it makes predictions, right? What kind of evidence could we look for?
Penrose and his team suggest looking for faint echoes from the previous eon imprinted on our cosmic microwave background, the CMB. One idea is Hawking points, unusually hot spots in the CMB, supposedly from supermassive black holes evaporating right at the end of the last eon. Another is concentric circles, faint rings of low-temperature variation in the CMB, possibly from gravitational waves generated by colliding black holes in the previous eon.
Right, I've heard about those claims, but it's fair to say they're controversial.
Very much so. While Penrose's group has reported finding potential evidence, the broader cosmology community has been quite skeptical. Independent analyses often conclude the signals aren't statistically significant, or they're consistent with just random patterns in the standard model of cosmology.
And there's still that huge assumption about all massive particles decaying, which we have zero evidence for.
Absolutely. That's a major theoretical hurdle for CCC. It's a fascinating, elegant idea, but speculative, and faces significant observational and theoretical challenges.
Okay, so bringing this all together, what does this journey tell us about convergence to a single point? The meaning has really shifted.
It really has. We started with the intuitive idea of a literal big crunch, the whole universe collapsing. That seems falsified by dark energy now, but gravitational convergence is definitely real in black hole formation. We see localized singularities there, at least classically, these points of no return.
Then quantum physics steps in.
Right? Quantum gravity theories like LQG and string theory suggest even that classical point isn't the end. It's replaced by a quantum bounce or a fuzzball. Convergence leads to a new quantum state, not oblivion.
And finally, CCC gives us this abstract geometric convergence at infinity.
A transformation linking eons. So the meaning has evolved from literal collapse to localized classical points to quantum transitions to abstract geometric mappings.
So looking ahead, what are the biggest unanswered questions? Where do we need to focus to understand ultimate convergence?
Well, number one is the nature of dark energy. Is it truly a constant Einstein's lambda, or is it dynamic, like quintessence? If it can change over time, maybe it could weaken or even reverse, potentially bringing back the possibility of a future collapse, big crunch or something similar. We just don't know.
And the other big one has to be quantum gravity.
Absolutely. We fundamentally need a complete theory of quantum gravity to truly understand what happens at singularities, whether in black holes or the Big Bang or a big bounce. Is it loop quantum gravity? String theory. Something totally new. That's arguably the biggest challenge in fundamental physics today. That's where the next breakthroughs in understanding convergence will likely come from.
So, to sum up, the big crunch, that universal collapse, doesn't seem to be in the cards based on current evidence. But gravitational convergence is very real in black holes. And that theoretical single point, the singularity, even though it's likely not physically real in its classical form, it's been this incredibly useful guidepost, hasn't it, pushing physics forward?
It absolutely has. It forced us to confront the limits of general relativity, the need for quantum gravity, and led to all these profound new ideas about the universe's fate, connecting gravity, thermodynamics, information. It's been a huge driver of progress.
So the ultimate fate of the cosmos and the final meaning of convergence, it really remains an open question. It keeps getting redefined by new discoveries and new theories. What new forms of convergence might future science uncover? It's definitely a question that keeps us looking up.